Sorry, I was waiting for you. Yes. Oh, no, we can, as you wish. Please give me 5 minutes, even 10.
Okay.
Okay.
But we're allowing 5 minutes for discussion.
Yes. I think I will be pretty fast, but you never know.
Okay, welcome back. Thank you for coming back on time. And now Nicola VITTORIO, strong evidence for
Okay. Good morning to everybody. I would like first to thank the organizer for the invitation. It's very difficult to talk after Alex for 2 reasons. First, because Alex is a very good speaker. Second, because we overlap quite a bit. But I hope to give a different view of some of these issues. I didn't go through the historical part. Just I wanted to remind that we have a cosmological constant now for 100 years. We have, in 1922, Friedman describing a mathematical solution. Was not a physical solution, but a mathematical solution. After all, Friedman was a mathematician. And we arrived to the 27th paper by Georges Lemaitre, which started after his PhD thesis at MIT, and also introduced what is been becoming the general relativity solution of Tolman in 1934, and by the way, by Bondi later in 1947. So what is the Lemaitre-Bondi, Tolman-Bondi solution that now has been discussed, and I will discuss a bit earlier. This has been mentioned. I'm always been very astonished by the title of this communication, The Beginning of the World from the Point of View of Quantum Theory, since this is a 31 paper, and since Georges Lemaitre was the Abbé Georges Lemaitre. He attacked the point of the beginning of the world is really something very, very important. What I always appreciate by Lemaitre is not to be in favor of concordism. I mean, to try to keep separate what is science and what is religion, and try to not to confuse the two. And he was saying that his scientific work never put in doubt his religion, faith, and vice versa, his religion, faith didn't never intersect with the assumption that he made in his work. And I think that, I mean, we can go on in that very, very, very deeply. Universe en expansion, as 1933 has been mentioned. So by the way, by that time we have all the ingredients to build up a model, which is the Friedman-Robinson-Walker metric, with the two-field equation giving the expansion and the acceleration. And here I'm using omega sub I just to indicate the density parameter of the eth component of the universe, either baryons or dark matter or dark energy, whatever you want. Omega k is the curvature density parameter, and P is an equation of state with double sub I being the prefactor that characterize the equation of state of the eth component. I will consider only constant values of V sub I for the time being, and I will be back on that. So what about these parameters? Has been already shown by Alex. We have a very strong constraints on the value density parameter, on the curvature, on the Hubble constant, and since omega lambda is larger than omega m over 2, we do expect that this model is predicting a low redshift and accelerated expansion. The first evidence, as was discussed by Alex was in late in the 90s, by the two papers by Rees and Perlmutter, and there has been an increasing evidence for an accelerating universe coming out from the supernova data, Betul et al. In 2004, the observational Hubble parameter, the baryonic relation, the consistency with the Planck measure means that a flat lambda CDM has been established as the concordance model. Is that the case or not? We will see later on. Let me talk a bit about the Jla dataset, which was the one that Alex showed, which is the most recent and the most numerous, consists of 740 supernova. The supernova has been 1A, of course, have been corrected by galactic extinction. There has been a change to the rest of the B band, the supernova rest frame B band. Technically has been processed in such a way to have light. Light curves as spectral filters from SALT, and so for each supernova we have a redshift, the apparent magnitude, the stretch correction in order to standardize supernova, and the color correction. And I want to touch upon the theory very, very briefly because, is there a pointer here? No. In any case, you have the luminosity distance that can be expressed in a dimensional way in terms of a unit of the Hubble radius. And if you define italic M as the combination of the absolute magnitude and the log of the Hubble radius, then you can express the magnitude redshift relation in this way. You see that the usual game is to fit three nuisance parameters, italic M, alpha and beta, much better, thank you. Which one? Okay, thank you. Here we are. Nuisance parameter, and then you have all the cosmology which is here in the luminosity distance. And recently there has been a paper which appeared in Nature by Nielsen et al., which proposed to consider a normal distribution both for italic M, for the color correction, and for the stretch correction. And in that sense, I think is a first step to introduce a distribution concept in the properties of the supernovae. Okay, they assume normal distribution, and in that sense, what we have is with 8 parameters to be fitted, alpha and beta that we had before, M0, C0, and S0, which are now the central values of the distribution, plus the 3 variances. So if you want to do that, you have to build up a joint probability of the intrinsic supernova parameters, in which you have for each supernova 3 numbers, essentially absolute magnitude, stretch, and color correction. You have central values, you have the covariance matrix, and if you want to build up a likelihood given a model, you may write the likelihood in this way. I don't want to enter in technicality, but let me just mention that. Nielsen et al. Claim that marginal evidence for acceleration, marginal errors less than 3 sigma. This approach was criticized by Rubin and Hayden in 2016, essentially because the approach, according to Rubin and Hayden, is incomplete for the selection bias that you have for different redshifts component of the supernova, and they presented the evidence for acceleration to be 4.2 sigma. Now, what I would like to discuss with you is one paper that we wrote recently, in which we were jointly considering JLA, OHD, BAO, and GRB observations. And what we want to test was K lambda CDM, which means a lambda CDM without the constraint of being flat, WCDM, which is a flat universe but with W not necessarily to be 1, a Milne model, some weird model which have been discussed by R equals CT cosmology, which is not an empty universe, but is a universe in which the combination of rho plus P is equal to 0, and more in general, a universe in which you have a power law expansion. Now, if you consider a K lambda CD model, so a model in which the curvature is not 0, but W is fixed to be -1, so cosmological constant. If you use only the supernova, the Jla sample, you have this gray confidence level here. And we agree, of course, with the Nielsen analysis. The idea is that you have the flat line here for a flat universe, and you have the dashed line, which is no acceleration today. So acceleration is up above, no acceleration is below. Now, if you take a best fit of the JLA alone, you get values which are for omega m over omega lambda. You see they're not summing up to 1. So there is a curvature, a residual curvature, which is in it. If you make a joint analysis of the 4 data sets that I mentioned, well, the confidence level is shrinked, and you can immediately say that a Milne universe, which is down here, 0 density parameter, 0 lambda, is completely excluded. Okay? Now, since we have from the CMB a strong prejudice for flat universe, let me move along the flat line, and let me explore another parameter space in which I have the prefactor in the equation of state, W, as a function of omega m. In this case, again, you have the gray confidence levels, which are the supernovae. Note that I cut the y-axis to -1, because I don't like to be below -1. And in any case, if you look to the axis corresponding to -1, you are perfectly consistent with the data. And with the supernovae alone, you may say that you are definitely in an accelerated way, because the no acceleration line is the dashed line that you have here. So even assuming a more extended statistical analysis by Nielsen et al., you can conclude that the universe has to be in an accelerated phase. Okay? And if you take the joint analysis, the level at which you can say that the universe is accelerated is over 5 sigma. And again, you may try to find best fit values, and for W inside the errors, you are definitely around -1. Now, let me cheat a bit. I'm honest on that, because I'm saying I'm cheating a bit. If you look to the red point here, which is W equal to -1/3, you have a universe which expands without accelerating, just CT, okay? So that will correspond to the RH equals CT models that Melia is pushing for, which is definitely outside the 95% confidence level. So I can anticipate it is not working at all. If you want to play with power law cosmologies, in which the scale factor can be written as a power of time, T to the n, then the standard Friedman model can be compared with the expansion rate you have in this kind of model, and then you can recast the Friedman equation to this if you assume that omega is equal to 0, omega lambda is equal to 1, a W is this combination of the index n. That is to say that if I want to work with flat power law cosmologies, are living on this axis. Okay? And then what we have found is that the best fit, we will see that in a second, for the shape, for the exponent of time, is just a bit more than 1, but it's very, very near to 1. And again, you can, from the joint analysis, eliminate that to the phi sigma level. What about the best fit models? Here there is R equals CT, this is power law, this is lambda CDM. Again, for lambda CDM, note that we get a value of H naught which is definitely lower than the value which has been quoted by Alex. I will be back on that in a second. But let me try to play the game of asking how RHCT is performing with respect to lambda CDM and how a power law with respect to lambda CDM. And in order to do that, we can use information analysis. You can use either AIC, which is a measure of the likelihood with the addition of the number of parameters that you have on the model, or a Bayesian information criterion, which they have the likelihood by a combination number of parameters and number of data. So if you compare the model with respect to the lambda CDM, I would expect the difference in the IAC to be less than 0 if the model performs better than the reference one, larger than 0 if the model is performed worse than the reference one. And you can see that the value that we get from the joint analysis are much, much larger than unity. So all these models are ruled out with respect to the lambda case. So the lambda is surviving. Note, however, that if I would have taken only the supernova data set, the power law for the supernova alone would perform in a similar way to lambda CDM. Okay? So the conclusion is, even if you want to consider a more sophisticated or a more general, not more sophisticated, more general statistical analysis, as Nielsen et al., definitely there is no way of avoiding acceleration. Now, the other point that I would like to add is connected with the estimate of H0 and the Hubble constant. And then let me talk about a paper that has been published in 2016. Now, the question is that there is definitely a tension between the value that is got from indirect measurements by CMB and the direct measurement by by measuring supernova and the calibration with the safe aids. So in order to try to disentangle the problem of mathematics, on purpose, what we want to do is to make a joint analysis only of JLA, which means supernova, OHD, which means expansion rate, and BAO, which means baryonic acoustic oscillation. We didn't consider the CMB here, okay? So if there is a systematic effect in the CMB, I should find from this data set something which is moved towards 73 rather than towards 66. So we did that on purpose. Let me show which are the results. I'm thinking I'm going pretty fast, but this is the situation that Alex showed. HST key project 72, RIS 2017, 73 plus or minus 1.8. WMAP, which means CMB, is 70, Planck 67. So what is coming out, the indirect estimates seems to be always lower with respect to the direct ones. Instead, you try to reanalyze the Rees et al. Paper. Clearly, the point is, as Alex has pointed out, stay tuned. Is there new physics behind this disagreement? Is the fact that you have an H0 which is systematically lower in the lambda CDM means that the lambda CDM is wrong or must be extended? If that you reanalyze the data, he found 72.5 plus or minus 2.5. Tension with Rees is reduced to 2 sigma. Say that there is no need for new physics. Let's see what we may try to do. Let me take a lambda CDM, so a flat universe, and let me try to make a different fit, supernova alone, OHD, JLA, and JLA plus OHD plus BAO, the joint analysis. Clearly, if I take the supernova alone, I have no way of measuring H0, right, from the high redshift ones. However, if I make a joint analysis, I may be able to measure even H0, because the supernova are not touching H0, but BAO and H of Z are measuring H0, and that is bouncing in the total fit with omega. Okay? So this is the result of H that we are getting from the Hubble, from the OHD, the Hubble expansion rate at different redshift. We obtain this value. From the BAO, this value. From the joint analysis, this value. And you may see that the difference with Planck is not great. There is an excellent agreement with Planck. So that suggests to me that there is not a strong, how can I say, effect in the analysis of Planck in terms of systematic, because if I use a different data sets, 3 different data sets, I'm getting a values of H0 which is pretty similar. I can do the same for omega m, but let me skip that. This is something that I can try to do assuming or relaxing the flatness of the lambda CDM. And again, what I'm getting is the blue contours are the supernovae, sorry, are the OHD data set, the orange are the BIO data set, and the green are the JL data set, the supernova data set. So you can see that we reproduce by the standard shape in which you have, by extension, the possibility of having a Milne universe, but I tell you that the joint analysis doesn't allow you to do that. If you take the space, the projection in which you have the Hubble constant as a function of omega m, you don't have the JLA, but you have this combination of BAO and H of Z, which is constraining this region a bit. You can do the same for the W. Again, if you look to the W as a function of omega m, you still are consistent with the value of delta W equal to -1. Now, one of the models that have been proposed in order to be, so to speak, alternative to the standard freedom model was to use the Lemaitre-Bond dissolution, to assume that you have a universe which is not homogeneous, although still isotropic. And the Lemaitre-Bond solution is described by a metric of this kind, in which the curvature of the spatial sector of the space-time is depending on the coordinate r. You can found the analogous of the Friedmann equation, in which you have all the quantities which are now depending on the center of symmetry from R, and then you can still define the Hubble expansion, you can define a density parameter, which is a function of R, a curvature, which is a function of R, and for each shell you have this usual constraint that omega m plus omega k is equal to 1. Now, if you have a void, the solution is pretty simple. It's just the solution of an open universe. The only difference is that the prefactors are depending on R, because you are in a universe which is not homogeneous, as Friedman, and you have a bang time here, which is due to the constant of integration, okay? If you take the bang time to be 0, then you start with a singularity. Simply you have different shells which expand in a different way because the energy of each shell is different because of the shape of the curvature. Now, in order to describe this solution, we need an answer for the matter density profile. We try to use several, and let me show you just the simplest one, which is just a Gaussian profile, in which you have a value of omega, which is the asymptotic one. You have a minimum in which is omega in, and then you have a characteristic size of the void. Now, in order to calculate and to fit with the data, in particular with the luminosity, with the supernova data, what you want to do is to write a magnitude redshift relation. And you can do that by following the photons which are arriving to us from a null geodesic. So you can define the luminosity distance in terms of the scale factor of the Lemaitre-Malbon dissolution, properly rescaled with the age of the universe. But at the end, apart technicality, you can build up something like that, in which, again, what you have to fit is italic M, alpha, stretch, beta, and C, as we have done before. Now, if you do that, you find a value of H naught, which is even lower than in the case of the Friedman model. Okay, the tension for the H naught is even lower. The value of the density parameter inside the void is pretty low, below 0.2, and the size of the void is pretty large. If you make the calculation for the best fit value from the JLL analysis, 0.61 corresponds to 2.5 gigaparsec. We cannot avoid that because the trick in using LTB is to use the fact that if you have a shape of the void, you want to have that shape to mimic the acceleration. So you want that shape to occur at a redshift at which the universe is showing the acceleration, which is about 0.7. If you want to compare this distance, you are in the gigaparsec scale. Now, again, I can try to use information analysis for this kind of models. For the lambda CDM, of course, is my reference point. For K lambda CDM, we have numbers which are of the order of unity, so we cannot really distinguish K lambda CDM from lambda CDM flat. WCDM, again, have number of the order of unity, so we cannot distinguish from different values of W different from -1. For LTB, we have quite large values, which means LTB are dead, I mean, as it is well known. But are dead essentially for two reasons, because the size of the void is too large and the value of H naught is too small. Now, let me be back to H naught. So what I plot here is a compilation of the best fit value of H naught that we can have, assuming a given model and considering different data sets. Now, if you consider LTB, LTB is in the low side, so it's not working. If you consider WCDM, you have numbers which are at about 66. If you move to K lambda CDM, you are definitely a bit better. If you consider the flat lambda CDM case, in which you have these three data sets jointly analyzed together, you are in extremely good agreement with Planck. So it seems that the CMB by itself, okay, which is quote-unquote high redshift data, and the low redshift data, which are supernova, BAO, and H of Z, are giving consistent answer. I mean, the H naught that you get from two different data sets are consistent. To me, that means that is, if you use the data as they are, if you want to fit a model to the data, consistently, whenever you use a model-dependent approach, you have an H naught which is smaller than the direct approach. Okay? This is something that has to be understood. But the point that these two data points are, that these two data points are so consistent is telling me that it's very difficult to think that there is some sort of systematic in Planck which has not been used, okay? Because different data sets are calling for the same value, which doesn't mean, to be clear, that there is a systematic in the direct measurements. Means that if we assume a model, you get something. If you make a direct measure, you do something. And so the real question is, what about the lambda CDM? Just to give you an idea, this is the standard H naught times omega m plot, in which for the lambda CDM you get exactly the same age. Interestingly enough, you are not far with the age from the LTP models, in the sense that you are getting something of the order of 13 gigayears, but the value of H naught is too small, so it doesn't work. So let me go to the conclusion, so I will have some time for the discussion. What we can say from the low redshift data alone. From the low redshift data alone, current expansion of the hour units is definitely accelerated. No way. No alternative models have been considered up to now. No possibility of having a power law cosmology, no possibility of having a CT cosmology, no possibility of having a Milne universe, which doesn't make any sense in any case. Now, the lambda CDM, if you want to stick to lambda CDM, is still the most consistent model with the observations. That means that it's the right model. I don't want to use right in this case, okay? So is definitely what we can use to say this is the most predictable, the most consistent, and definitely constitutes the baseline for a concordance model. However, there are open issues, as Alex was mentioning. First of all, what does it mean lambda? What is lambda? What does it mean dark energy? What is dark energy? How do you model dark energy? Why omega lambda and omega me are equal? 0.3 and 0.7 to me is the same. So why we have an accelerated expansion today? Why lambda is so small compared to the reference value that we have from particle physics? And why model-dependent indirect estimates of H naught are not consistent with direct measurements? So I think that what Alex was saying, stay tuned, is essentially in the second step. I mean, we don't have definitely answer to that. And then I left some dotted line here that I'm sure we will discuss in much more detail. I'm not an expert at that, which, for example, has to do with the considering that after 100 years of general relativity, it may be something that generalize general relativity, some modify gravity. And when you're talking about dark energy modify gravity, you are talking about something that is difficult to distinguish, because it depending where you put the extra term, either on the left or on the right of the equation. So I think I would stop here. Thank you.